Hello everyone, I am very happy to have the opportunity to present a part of my PhD work today. I'm doing my PhD at the ESPCI in Paris in collaboration with the startup Sense Detectors Care. During this PhD, I'm mainly working on body odor in the context of healthcare monitoring, but today for this presentation, I will mainly focus on how to avoid the pitfalls of intra-individual variability and sampling environment contamination. But firstly, before going into details, I'm going to explain what body odor is. Body odor is a very complex matrix. It's composed of at least 500 volatile organic compounds, and those molecules can come from very different sources. Some of those molecules will be linked to genetic parameters, and at the opposite, we can also find molecules linked to 100% exogenous parameters such as cosmetics. In between of those two categories, there are also molecules linked to more variable factors such as diet or pathologies. So indeed, it has already been proved that pathologies like diabetes or epilepsy have an effect on our body odor. But lately, in this presentation, we will talk about COVID-19, which was our first clinical study. But before going into detail, we can wonder what exactly is happening to our body odor when a pathology affects it. The first thing is that there are some changes that will be produced regarding our metabolic activity. Some reactions that were usually happening in our cells will be modified, and thus specific molecules called metabolites will be produced. Those molecules will travel in our body and end up their trip in already well-known and well-studied matrices such as blood, feces, or urine. But some of those molecules will also succeed in passing the barrier of our skin. They will meet our skin microbiota, and at this stage they will become part of our body odor. So this is why in this project we are interested in detecting those variations of body odor, and to do so we considered two methods of detection. The first one is the canine detection, and the second one the analytical detection, which is obviously my part of the job. All of that in order to identify specific volatile biomarker of pathologies. So for our analytical approach, it is as follows. We will trap the VOCs emitted by the sample individual on a sorbent phase. Then we put the sorbent phase inside an empty thermodesorption tube, and then we analyze it thanks to thermodesorption, followed by a comprehensive two-dimensional gas chromatography, affiliated to time-of-flight mass spectrometry. But the sampling phase is not as simple as it seems, and this is why it took us 2 years to develop a sampling system that allows to have reliable results. For example, we tested many raw material in order to identify the one that is not already containing a lot of VOCs. So unfortunately, I won't be able to talk about this sampling system in much detail because it will soon be patented, but it will also soon be produced on a large scale. So good. Now we are able to obtain a body odor sample, and here is its corresponding chromatogram. And we are not afraid anymore that the peaks we are now observing could be linked, for example, to the glue of the dressing film used to fix the sampling system, for example. But still, it's body odor, yes. But what is exactly inside that body odor? Are those peaks related to the cosmetics, to the bacterial activity, or to our genetic parameters? It was important to us at this stage to understand a bit better this matrix, and so to understand the body odor. So our first step was to identify the effect of cosmetics on body odor. For that, we decided to launch a small-scale study and to sample one individual during 1 week with, at first, unchanged cosmetic habits. We sampled this individual from the 2 armpits 3 times a day, and as I said, for 1 week. Then we asked this individual 24 hours before the first day of sampling and for the day of the week to stop using cosmetics such as deodorant and perfume. And then again, we sampled him from the 2 armpits 3 times a day for 1 week. Our goal after that with the obtained data was to identify peaks and so molecules that could be specific to a body odor with the use of cosmetics and without. To do so, we use the software chromatography, and I checked manually the given hits in order to remove the one that could be linked to noise, for example, but we also decided to remove the hits without any attribution. So it finally gave us 85 molecules confirmed manually. Then we were interested in classifying those 85 molecules into categories, and we did that according to the pattern of evolution. You can see here for the first molecule, for example, that this molecule is observed when the cosmetics are used and then it disappears. Same here, but less fastly. So this is why those molecules were attributed to the cosmetic parameters, because they were present when the cosmetics were used and then they decrease more or less fast. At the opposite, we can see this kind of molecule that was not really observed when the cosmetics were used and then tend to appear when cosmetics are stopped. At this stage, it's important to know that cosmetics such as deodorant are also called bactericides, or at least we know that they can inhibit the bacterial activity, and this is why the molecule which have this kind of evolution pattern was attributed to the bacterial activity. Moreover, this molecule specifically was also already cited in a literature study, in an in vitro study, and as a compound produced by the bacterial activity of Staphylococcus. So it's great because here we seem to have proved that it's true, but thanks to an in vivo study. So in a second part, as we previously obtained only armpit samples, we decided to investigate the homogeneity of body odor, and to do so, we sampled one individual in 4 different body areas: the armpit, the upper back, forearm, and the groin. Here you can see the number of detected compounds per sampled body area, and we can see that the highest number obtained was for the armpit. In the second place, there is the upper back that is here, but at this stage it's important to note that for this small-scale study, we asked the sampled individual to stop using deodorant and perfume, but not hair care product. And it's important to notice that this kind of product are more likely to fall in this part of the body, so in the upper back. So this could maybe also explain this obtained number. Then we investigated, but without doing an exhaustive study, if we can see a molecule specific to some body areas and molecule that could be present in the 4 sampled body area. It was the case with here, for example, isoxazole, which was only present more present in the armpit, and benzotiazole here, which was present in the 4 different sampled body areas. So we identified different molecules like that, and so there seems to be a stable and a variable component within the body odor. After that, as we previously identified 15 molecules as pertaining to the bacterial activity, we decided to see if those molecules were really specific to the armpit, or if we can also find them in the other sampled body areas. So among those 15 molecules, only 5 belong only to the armpit, and among the others, we can see the example here of acetoin and butadiene, which was firstly highlighted thanks to armpit samples, but we can also find this kind of molecule in the groin area. So those molecules seem rather specific to areas with mucous membrane, high density of sweat glands, and so a possibility of maceration. Finally, in a third part, to understand this beautiful matrix that is body odor, we decided to investigate the stability of body odor during time, and here during 1 week. So we sampled one individual, and again we used chromatography in order to look for a compound that could vary significantly over the course of the week. At this stage, we became quite surprised because the highlighted compounds were chlorinated one, and according to our knowledge and also literature, there is no reason that we could, as humans, physiologically produce this kind of compound. So we wondered what happened between Tuesday and Wednesday for chlorine compound to appear in the body odor of this individual. So the first step was to ask the individual what he could have done, and in fact he went to the swimming pool on Tuesday. So on Tuesday night, as he was going to the swimming pool, this was a first clue, and we also have a little knowledge on organic chemistry, and we know that the chlorination reaction exists. This is an electrophilic aromatic substitution, and so we wondered if this could have happened. So we look for the non-chlorinated analogous for the observed molecules, and we found them because we found acetophenone and benzaldehyde, and chromatography highlighted the chlorinated analogous. So we looked at the pattern of evolution of those molecules, and here we tend to see that when the chlorinated compounds appear, there is a decrease for the non-chlorinated one. So there seems to be a consumption of the original body odor compound that seems to react with the chlorine inside the swimming pool to produce this new compound. So now, finally, now that we have understood a bit better our matrix, we are going to talk about the first clinical study that we launched. It was on COVID-19, as I said during the introduction. During this clinical study, we sampled individuals, both tested positive and other tested negative to COVID. And after that, we elaborate a whole research methodology in order to tend to highlight a biomarker. At first, we did that only for the armpit sample in order to compare things that were kind of coming from the same part. It gave us 7 potential volatile biomarkers, and here you have the example with the potential biomarker that is M15. You can see a 10-time fold between the mean area found in a COVID plus group compared to the COVID minus group. But we became quite suspicious. So we became suspicious because in fact all our COVID positive individuals were sampled at the hospital, and we knew that all our COVID negative individuals were sampled in our lab or in the canine training center. So we wondered if this sampling environment could have an influence on the sample itself. So this is why we were suspicious. So we decided to sample the air of the hospital, and here we saw that it was approximately at the same amount than for the COVID minus group. So the M15 wasn't in the air of the hospital. But then we sent a COVID negative individual in the hospital to be sampled there. And here we saw that the M15 compound increased. So finally, we didn't have marker of the pathology, but we rather had a marker of the exposure to the hospital environment. And finally, no potential biomarker left. But as I said during the introduction, for this project, we have 2 detection methods that are considered. So what about dog detection on that are doing on the same type of sample? In fact, they got 100% of correct detection, and that regardless of the sample body area. But dogs they are not talking to us, so what are they detecting really? Are they detecting the smell of COVID, or the smell of the hospital environment. To try to understand that a bit better, we decided to acquire the COVID negative samples taken this time in the hospital, and then we submit them to the dog detections. And here you can see one of our dogs testing the samples of COVID. The results were quite impressive because, again, still 100% of correct detection regardless the sampled body area. So there appears to be one or more molecules specific to the pathology and common to the sampling areas, even if analytically we didn't seem to saw it. So in order to not throw away all our data without any conclusion, we went back to our research methodology, but this time with a new processing. We decided to use the new hypothesis given by the dogs, and we took all samples from positive patients, and they were combined in the same group, whatever the sampling area. So we've really used all our data. This time we got 24 new potential volatile biomarkers, but we also gain in knowledge. So we decided to use that. And among those 24 new potential volatile biomarkers, we saw that 12 were probably linked to cosmetics. We knew that because they were cited in cosmetic studies or in the composition of cosmetic products. We also saw that 7 were probably linked to the surrounding environment because those potential biomarkers were overexpressed in the COVID- group, but only for the individuals sampled in a big city, that is Paris, and not for the negative individual that were sampled in the canine training center that is in the countryside. So it seems to be linked kind of to pollution and so to the surrounding environment. So we put that away. But still, it means that there are 5 potential volatile biomarkers left. And as we now know that we seem to be able to trust the dogs, it will be confirmed as to be a real COVID biomarker or the exposure to the hospital again. And we will answer that question by using a synthetic ODOR mixture and submit it to the canine detection. So to conclude that presentation, it's a good thing because now we have a better understanding of the body odor metrics, and it's very important. We know that some VOCs are linked to cosmetics and some others to bacteria activity. There is, concerning the homogeneity of the body odor, there is a stable and a variable component inside it. And the influence of the surrounding environment is real, and it's very important to take it into account during the clinical study, for example. Concerning the COVID-19 study, there is now a possibility to further exploit the results thanks to the combination of the canine and the analytical detection, so it's quite powerful. But those two detections have different needs in order to achieve reliable results. Now we have 5 potential volatile biomarkers, and we will need to study them in more detail. For the things that are coming soon, we will soonly launch a clinical study on skin cancer with a protocol that is now taking into account all the identified bias factors. First important thing, we will use our new sampling device. We will also try to remove as much as possible the cosmetics, and we will also sample the surrounding environment, and also LC and 6 subjects will be sampled at the same location. I would like to end that presentation by thanking the LSIBM team, Sense Detect Healthcare, and all my collaborators, and of course you for your attention. Thank you very much.